Alright, so in this lesson what we're going to mainly do is start looking at the integral and how integrals play a role in physics. So first of all, what is an integral? An integral is very similar to an antiderivative. I actually think of it in some ways being the same thing. I would actually say antiderivative and indefinite integral are exactly the same thing. What an indefinite integral basically says is what function can you take the derivative of and get the function of the thing that's inside the integral. So if you want to indefinitely integrate a function, it's basically saying what function is this function the derivative of. In the case of a definite integral, we're usually looking at a very specific value. And a good example of what a definite integral would look like is on the right here. We have some function y equals f of x, and I've defined a region between x equals a and x equals b. And so if I wanted to figure out like what is the area of the shaded region for an example, I'd use an indefinite integral to do that. If I wanted to find volumes, indefinite integrals are usually used. Dealing with distributions of masses or charges, those are good examples of definite integrals. In most of those cases, this would be particularly true if the distribution of mass or charge is not uniform. Integration would be probably the best trick to deal with that. So let's look at some indefinite integrals. Here are what I call the indefinite integration rules for basic integrals. Here I have the power rule up at the top, x to the n dx. In that case, you get add 1 to the power, divide by the new power, and add c. Note this doesn't work for the power -1, but it would work for all other negative powers, say -2, -3, so on and so on. This rule would also work for things like square root or 1 over square root as well, because you can write square root as a power. I have the e to the x one. I have dx over x plus a. That's your n is equal to -1 case, in which case you get natural logarithm. And then I have cosine and sine. So this is a set of kind of the common indefinite integrals you come across in physics. Now, of course, you might say there are other integration rules that exist, things like u du substitution, which is really a way of undoing the chain rule, or UDV substitution, which is really a way of trying to figure out how to undo the product rule. There are other tricks in integration or other rules that we might run across. We're mainly concerned about the basic ones because a lot of the stuff we come across in AP Physics is real basic integrals. So what I want to do first is have you solve a set of indefinite integrals using the rules. I think the best thing for you to do is pause the video for a couple seconds and try these out, and then we'll actually look at the solutions together. So hopefully you've paused the video, tried these and worked these out on your own so we can actually work through them together. The first one would be x cubed over 3 minus x squared over 2 plus 2x plus c. Now it's worth pointing out that when you add or subtract, kind of like differentiation, you can add and subtract integrals. This could be rewritten as the integral of x squared dx minus the integral of x dx plus the integral of 2 dx, which is what I get here. Second one, I should get negative cosine of 2x plus c. The next one, I should get 2 times e to the x over 2 power plus c. And then the last one, I should just get natural logarithm of x plus 3 plus c. The way to check these is take the derivative of the thing you have and see do you end up with the thing that's inside the integral. So let's look at definite integrals. These are generally the ones we're going to come across in physics. And they have an upper and a lower limit or an upper and a lower bound on them. Sometimes those bounds might be something like infinity or negative infinity. That would still be a limit that we could use in order to define that integral. There are some instances when we're working through a problem we realize we need an integral that probably the hardest part of the problem is setting up the integral itself and deciding what limits make sense for that problem. When we get looking at some applications of integration, we'll see, in my opinion, I think that's probably the hardest part of doing these types of problems. So let's look at a problem, and I have a car that's going to undergo a nonlinear acceleration given by the function a of t is negative 2t plus 4, where a is measured in meters per second squared and t is in seconds. At times t equals 0, the car starts at rest. That's an important piece of information because that's an initial value. Basically, it says when you're finding v, if you plug 0 in for t, you should get 0 for v. It's really a way of telling you what the what that constant of integration c is. And it wants to know what is the function for the car's velocity and what is the car's displacement between the times t equals 3 seconds and t equals 6 seconds. So the first one, what is the function of the car's velocity, that's really an indefinite integral problem. So let's figure that out first. Velocity would be the indefinite integral of acceleration, because acceleration is the derivative of velocity. So if we plug that function in, what we end up with is the function negative t squared plus 4t plus c. Now I said this value of at time t equals 0, the car starts at rest. What that allows us to do is calculate the value of c. So we can find c, and the easiest way to do that is plug 0 in. It started at rest. Plug 0 in for t, and what you fairly quickly figure out is that c is 0 in this case. And so really, the function for velocity is negative t squared plus 4t. Now in the second part of this problem, what is the function, or what is the car's displacement between times t equals 3 seconds and t equals 6 seconds? That's really a definite integral. And the way to set this up is to say x is equal to the integral of velocity. And if I want from t equals 3 to t equals 6, that's how I'd set this up. And so what I would do is integrate it. Negative t cubed over 3 plus 2t squared. And I'm going to evaluate that from t equals 3 to t equals 6. Now you'll see sometimes when I write definite integrals, I'll put a line and then numbers on the top and the bottom. On the bottom of that line is my lower bound, and the top of that line is my upper bound. That's just my code for myself how to do it. Sometimes you'll see this t equals 3 to t equals 6, something like that. What this would mean is I plug in t equals 6 in, and then subtract the value of the function at t equals 3, and what I get is the displacement between t equals 3 seconds and t equals 6 seconds is negative 9 meters. Don't get concerned that this is a negative number. What this means is from t equals 2 seconds to t equals 3 seconds to t equals 6 seconds, this thing went in the negative direction 9 meters. So that's kind of some quick introduction of some basics with integration. We'll look at in the next couple of lessons is some very specific applications of how we use integration to do some problems, or how we define what's called a differential equation and what that actually says about a system or a situation.